All right, welcome to circular motion. So before we do any note-taking or anything, we probably want to watch something move in a circle. And here we have me twirling a ball on a string in slow motion so that you can actually see where the ball is and how it's moving at each point along the way. We can continue watching this, or we can mosey on ahead, which is what we're going to do. And get to the important stuff, some of the basics of circular motion. When we're talking circular motion, we're talking about an object moving in a circular path, which is what you have on your handout and what we have on the screen here. This is supposed to be representing the ball from the video, and when you were watching that video, I might ask you the question, what was the direction of the ball? Well, words like right and left don't really work in this situation. And in our case, the video you just watched, it was definitely moving in the clockwise direction. Alternatively, the other way it could have been moving is in the counterclockwise direction. So it's important for us to understand which one is positive. In the same way that up is usually considered positive and down is considered negative, we've got to figure out which one is positive and negative for clockwise and counterclockwise, which means we're going back to everybody's favorite, the unit circle. So just a reminder that the unit circle, it defines a 0-degree angle to be at the perfectly 3 o'clock position or the farthest right position, however you want to describe it, but we are currently at angle equals 0. Now, as we go around the unit circle, you'll notice that we go to the positive 90-degree angle, and then the positive 180, the positive 270, and we get back around to the 360-degree. So which way did we go around that? We went counterclockwise, which is why counterclockwise is considered the positive direction, think unit circle. And that means clockwise, negative direction. So we need to think about our circular motion. And so I'm going to pick to use a counterclockwise because I'm not there to ask which one people want to use, and I want to use the positive one. And we have to look at the ball at specific positions. I'm picking the top, the two center positions where they're at the far right and far left, and the absolute bottom of its path. Now, when we do this, we want to ask which way is the velocity going? And if you remember, velocity is always tangent to the path that the object is taking. So at the very top, if we're going counterclockwise, that means the velocity is going to the left. At the far left position, the velocity would be going down. At the bottom, it's going to the right. And at the far right side, it would be going up. Perfectly clear, we've got that going on. Now, why is the thing moving in a circle? It's moving in a circle because it's being pulled by a rope, and ropes can only pull. Remember that. So what's the direction of the rope force, or we called it tension? Well, remember how it depends on where the actual rope is? At the very top, the rope is below it, so that means that the tension is pulling down. At the far left-hand side of our image, it's going to be pulling to the right. At the bottom, it's pulling up, and at the far right-hand side, it's pulling to the left. So we've got the forces going in all the way around, looking through all of this. Now, in terms of motion, in addition to velocity, one of the other important things we talked about is acceleration. And Newton's second law informs us that if F equals ma, that means that the acceleration and the net force are absolutely positively, without exception, in the same direction. So adding in our accelerations is going to be a relatively quick and easy thing. Now, since the acceleration technically changes directions when we use words like up and down and left and right, it's going to be really helpful if we get a description of a direction we can talk about for all of these things that at every point along the way, at any point along the path. And that would be towards the center or inward. The technical term for that is centripetal, which literally means center seeking. Now, we're talking acceleration, so I wanted to remind you of a few things, and this is that whole back to August. Accelerations, by definition, are a change in velocity over a change in time. In other words, we have to have velocity changing. In order to have velocity changing, and we're describing this to a 5-year-old, remember, we can go faster, which means the acceleration and velocity are in the exact same direction as each other. We can go slower, where the acceleration and velocity are oppositely directed, and we can make a turn. And that's where the acceleration and velocity are perpendicular. Okay, we didn't talk about the perpendicular stuff, but we did talk about the fact that turning or changing directions is an acceleration. This unit is all about the turning, the circular motion. In other words, it's about the centripetal acceleration, which is depicted as a sub c. Centripetal accelerations are required to make anything, anywhere, ever move in a circle. And they're always directed towards the center of the circle. The value of this, to derive how to get the value, is a little bit complicated. The easiest way to do it is with calculus. So I'm just going to give this to you. This is a trust me moment, that the centripetal acceleration has a magnitude equal to v squared over r, where v is the speed of the object and r is the radius of the circle. Now, we have uniform circular motion. We have a bunch of equations that we're going to associate with it, but it's probably important that we also get the definitions. So they move in a circle with a constant radius of capital R or lowercase r. They also move at a constant speed. That's what the uniform means, constant, the same. That speed is going to be, remember, distance over time, so the circumference over the period, and it's always directed towards the center, that centripetal direction. And remember that period, if you don't remember this from maths, or better yet, where we're going to redefine it to be more specific in our class, is the amount of time it takes to complete exactly one cycle. Since it's a time period, time unit, are going to be seconds. Closely related to period, but not the same thing, is frequency, which is the number of cycles in a given amount of time. So when we're talking about circular motion, those units would be revolutions per second, or RPS. When it comes to the equations, the equation of velocity or speed being 2 pi r over tau, or the circumference over the period, totally makes sense. Going to use that a lot. The definition of the centripetal acceleration is v squared over r. The devil equation, that period is 1 over the frequency. While this is an absolutely true relationship that is on your equation sheet, I hate this equation because it's way too easy to get period and frequency confused with one another. Please, please, please focus on the actual definitions written in words on this page. Now, the time has come in our adventure together where we're finally going to be having some generic answers for equations, like derive an expression for something. You're going to make your own equations, and I know how excited everybody gets about purely letter answers, and I get it. It can be hard. So I have a little bit of a suggestion as to how to approach this. When we're going to be creating our new expressions or equations, we want to start by using an equation from the equation sheet or a basic definition. Then we'll substitute in with a different equation into that already established equation instead of subbing in a number. So circular motion is just an extension of forces, so this is a total Newton's second law situation, that force centripetal is equal to ma centripetal, which would be equal to the forces going in towards the center minus the forces going out. Good news, in honors, we eliminate all outward forces because I limit our situations to ones where the inward forces are only being caused by tensions, which means there's a rope attached to the thing. Gravity, which is only when things are orbiting, like a sun or a planet or something like that. And for everything else in our class, it's going to be friction is the reason that things are moving in a circle. I get it. There are thousands of other examples, but I wanted to limit it so that we're not totally overwhelmed. Once we establish what is causing that inward force, then we'll substitute in, instead of 8, we'll move out the AC and plug in the v squared over r, and then we can plug in other equations as needed, like subbing in for velocity as 2 pi r over tau. If we have frequency information or we're looking for frequency information, we can also use the Devil equation that period is equal to 1 over frequency. And we can use things like friction, that the force of friction is mu times the normal force. I think you get where I'm going. Now it's time for you to do some problems.